So today it's a pleasure to welcome our speaker, Professor Mathias Klaui. He's Professor of Condensed Matter Physics at Johannes Gutenberg University in Mainz. He has a research interest that focuses on nanoscale magnetism and novel materials. He works at the interface between basic science and applied research and has a great interest in some of the societal implications of his work. He did his first degree in Aachen and then his PhD here in Cambridge at the Cavendish Laboratory and then various positions in Zurich and Constance before his present post in Mainz. There he is the founding director of the Gutenberg Council for Young Researchers and director of the Graduate School of Excellence in Material Science. He's fellow of the Institute of Physics and has received various prizes for his work. And he's also a fellow of the think tank on renewable energies and low power IT devices. So he's perfectly equipped and skilled to give us the talk today on technology for a technology for a sustainable world. Welcome.
Well, thanks a lot for this really nice introduction, and it's always a pleasure to be here. So this is already the second talk that I'm giving at the Faraday Institute. So I was here for the first time about a year ago, which directly leads me to my first apology. There's at least one person who has heard large part of this talk already. I got feedback last year that people liked it a lot, so I decided that I will only have minor modifications to it. So you'll hear a slightly updated version of this. I'm indeed Mathias Klaui from Johannes Gutenberg University Mainz, and I'm a physicist, so I'm not a climate scientist, so you'll hear a lot about climate change, but I'm not doing research on that. What I'm really qualified for formally is condensed matter physics, which is kind of the second part of the talk, i.e. how can we actually save energy. So very briefly, the outline of what you can expect in the next, I was told, exactly 45 minutes. So a little bit about climate change and consequences, just to make you all aware of why I actually have chosen this topic and why I think this is important, and actually part of the reason that I've chosen to work on what I work on. Then sources of CO2 emissions and mitigation strategies. This is how can we at least try to, if not fix, mitigate the problem. And then it comes closer to my own research interest, the reduction of energy consumption, and here the role of information technology. And finally, recovering waste energy, how to actually use a lot of the wasted energy. But before I do that, just one slide on myself. And so I have chosen to show you the churches of the places that I came from, and just to keep you on your toes. Anyone knows where this church is? Anyone knows that? So it's the largest church in Zurich in Switzerland, the Großmünster. So that's where I was born and partly grew up. And then I did my undergraduates at this place here. Anyone knows where this church is? Aachen, exactly. Yes, at the University of Technology. So I'm impressed. So it used to be the center of Europe under Charlemagne's reign. And then I guess most of you will recognize this place. So who knows where this is? It's what? It's here, so who knows this? Chapel, Wren Chapel? Pembroke, exactly. So that's where I did my master's and my PhD, and most importantly, got to know my wife. That's why we have fond memories of Cambridge, and now I'm here. One of the largest Romanesque cathedrals in Europe, which is in Mainz. Yeah, so I'm now working at the university. I'm director of material science and professor in condensed matter physics, and I'm interested in science and faith for a sustainable world. All right, that's my own research, my own pedigree, so to speak. So what are our challenges? What's the problem? So here, just a few of the cover pages of various journals in the past 20 years or so. Obviously, it's an important topic, but what I find more compelling to do things is not these pictures, but these pictures, because this is something that at least for anyone, I think, with a heart, leads to compulsion to actually do something. So where does it come from? So it comes from here. So it comes from these guys, which all died and turned into coal and oil, and primarily not the people, not the animals, but the plants. So we have here a lot of stored sunlight. That's energy that is turned by the plants into something that can be stored, so coal, gas, oil, and that energy can be retrieved by burning that. That's good because we have stored energy, we get the energy back, but it has some side effects. So the side effects from burning this 200 to 500 million year-old energy in fossil fuels is that we increase carbon emissions. So in particular, carbon dioxide. So this is famous Mauna Loa curve, which was collected from ice, where you see that, so this is measured Mauna Loa since 1960s, and you see that the concentration of carbon emissions is kind of continuously going up. By the way, the little yellow ups and downs, that's simply the annual cycles, and the red is the smooth curve on the average per year. And about 80% of that comes from industry and about 20% from deforestation. And we're kind of lucky because there are a lot of things in the world that like carbon dioxide. And that's all the plants, algae, and so on. So about half of this emitted is absorbed by the biosphere and the oceans. Without that, we'd be even in more trouble. So kind of the global biosystem is absorbing a lot of our additional CO2 because obviously it dwells on CO2. This doesn't look so bad because it's only the last 30 years. Let's look at the more global scale and this comes from ice. So this is ice domes where they extracted the composition of the atmosphere over the last, in this case, 20,000 years. And what you can see, it kind of all wiggles up and down until very recently. And essentially, this recently, that's us. This, is okay. Well, the carbon dioxide goes up a little. Apparently, there are some natural causes that increase carbon dioxide. It flattens off. Methane, goes up and down. Has to do with the ice ages and so on. And nitrous oxides, again, it goes up and down. And in the end, something happened, and this is what happened. That's human. I'll show you why, where this comes from. Now, what is important here is if you now compare these curves to this curve. This curve is the population. So also, not much happened until quite recently, and that's when our world, in terms of population, exploded. And this is quite correlated, and I'll show you in a minute where it comes from. So one of the things I wanted to discuss with you is energy, because we burn fossil fuels to generate energy, and obviously, if you look at global energy poverty, there are places in the world where there are a lot of people without electricity and without clean cooking facilities. So in Africa, of course, in the Indian subcontinent, in Asia in general, China, South America. Now, if I look at this, I can ask you, do you believe in climate change?
It always has changed.
It absolutely always has changed, but yeah. Actually, I don't believe in it because faith is the substance of things hoped for, the evidence of things not seen. So, and I think we can clearly see climate change. So in that sense, I don't think it's a question of faith if there's climate change or not. There is climate change. And I think there's also, it's not a question of belief that there is human-made climate change. So where does the increase in the CO2 emissions come from? So there's a big CO2 emission, or not just CO2, but also nitrous oxides, methane, and so on, which is industry. And if you look at who is doing it, it's us. So Europe, North America, Asia. So that, we can always say there's deforestation or whatever, but that's primarily us. And there are a lot of activities that are going on, from burning coal to different chemical plants that do lead to the emission of CO2. And some of it is inevitable. So there are questions of what can you do with it? Can you somehow store the CO2 that you emit? Some processes can be improved. Some of the things, for instance, burning coal, there's a question if we really need to burn coal in the long-term future. Now, if I go back to the slide about energy poverty, and compare this, then essentially the CO2 emissions from industrial processes come from the places where we don't have global energy poverty. However, if we now look at the second large contribution to CO2 emissions, so-called land use changes. So that's essentially deforestation, changes of the land use, i.e. replacing something where a lot of CO2 was bound in wood, for instance, by something where there's little CO2 bound, and that difference usually goes up into smoke. So if I look now at the CO2 emissions from land use, it kind of is complementary to the CO2 emissions from industrial use. So there's very little in Europe, a little bit in North and Central America. It's primarily Central America, but there's lots in South America. That's the deforestation of the Amazon forest. There's Africa and in Asia. Now, if I now compare where there is lots of deforestation with the global energy poverty, I see that actually where people have a lot of deforestation, they still don't have energy. So this means fossil fuels are not the answer to solving poverty. So you just come back to that important argument. So there is a lot of deforestation going on. So there is a lot of energy being produced by burning wood or burning coal. However, it does not help to have energy for the people. So it's kind of a double waste. You burn the wood, but you don't help the people with it. So fossil fuels are not the answer to solving poverty. I think this is pretty clear. So just improving access to fossil fuels will not solve the problems. So now let's look at the consequences of climate change. So far I only talked about emissions, CO2 emissions, methane emissions whatsoever. And if we now look at the temperature, and that's the temperature anomaly, meaning that how much does the temperature change compared to the average over 100 years ago, then you see roughly 100 years ago, things started to go up. And this is directly correlated with industrialization. Industrialization, for that we burned a lot of wood, generated a lot of CO2 emissions, other emissions. We had a lot more people suddenly because we could afford to have a lot more people, and this led to an increase of the temperature rise. And just, because this happened not so far from here, so hacking into scientist emails does not make the evidence go away. So I don't know who came up with that idea, but there is, as a scientist, I can tell you that evidence doesn't go away by forging emails. Now, more importantly for England, so what can you learn from this? This is the maximum central England temperature and daily mortality in 2003. I don't know about this year. Did you also have a very hot summer this year? Yeah. So I would like to get the same data for this year, but I couldn't find it. But I can tell you, if it's hot, English people die. That's the key message. By the way, Germans and Swiss as well. But I had the data for England. So this is the maximum temperature. And so what you can see is that when you have a peak in temperature on these days and these days, a day or two later, English people die. So mortality goes up significantly. Yeah. So even in a developed country like the UK, like Switzerland, like Germany, it is dangerous to have hot weather. So
otherwise I just shout. Okay, key message is hot temperatures are dangerous for us, particularly for the elderly and the very young. But the question is this a problem if it happens once every 20 years? It's less of a problem if it happens once every 20 years, but likely by 2040 it will be the norm. So by 2040 we expect that this type of hot weather as we had this year, as we had 2003, will be the norm rather than the exception. So this is the spike that you see here, the 2003 spike, and the models predict that by 2040 this will be the average summer. So why? So let me just go back, and I think I would like to explain this to everyone. I mean, I guess you're not all scientists. So who's a natural scientist? Okay. Well, there are lots of people that are not natural scientists. Perfect. So let me give you a very, very simple spiel about where this problem comes from. And it is really surprisingly simple, and few people know. So what happens is we have the sun. The sun radiates at us. Actually, today is a great day, so it's, I would say November in Cambridge is not always that great, but this is fantastic. So the sun radiates light and electromagnetic radiation at us, And the Earth partly absorbs this and makes heat out of it, and partly it reflects it. However, this reflection of the light is not always going out, but is actually reflected by CO2 gases, by molecules and clouds, so greenhouse gases like CO2 and methane and so on. And so essentially the light that is turned into heat, the infrared radiation, cannot go out anymore, but is reflected back to the Earth like ping-pong effect, which essentially makes a greenhouse work. Greenhouse works because the incoming light, the visible light, goes through the window, but the generated infrared radiation that comes back doesn't go back out, but stays inside. And this is what our CO2 does. So if you have more CO2, we have better glass windows, so to speak. And this means if we have more CO2, we'll have more heating. Very, very simple. But that's exactly the main effect. So what are the effects of climate change? Why should we bother? Apart from English people dying, Swiss and German people dying, there are lots of other effects which are not good. So essentially in southern Italy we now have malaria-carrying mosquitoes. We have more extreme storms, floods, droughts, heat waves, which lead to water and food insecurity, may lead to migration and conflict, and may lead to significant changes of a habitat for all. So here, if I look at my Bible, and it says, "And God spoke, let make human beings in our image, make them reflecting our nature, so they can be responsible for every living thing that moves on the face of the earth." This is an issue. Now, what we here do is not what God wants. And there is no single number where you say, like, if we have a temperature increase by X degrees, then everything will break down. But more is worse. I think that's a clear thing. We know that if you have more temperature rise, things don't get better. Maybe the quality of the red wine in the UK does, but that's a minor point. So in 2009, politicians agreed on that we should have a maximum of a 2-degree temperature rise by 2100. We're already failing at that. So if you look at the moment, we are on track for a 4 to 6 degree increase by 2100. And this is predicted to mean that we have to spend a significant amount of our GDP for disaster mitigation. So this means that we'll have to spend a significant amount of our GDP to actually cover for droughts, for floods, for storms, and so that we expect. And so, one can laugh at this, but unfortunately it's something one really has to tell people. Many of our friends, family, and people that we are in touch with think if the commentator on TV says, after a comprehensive review of a climate science, we have concluded that climate change is 99.5% certain and not 100% as we previously stated. So 99.5% is pretty good. For everything that I do in my life, I go with 99.5%. So then people always come to you and say, like, but weather forecasts are not very reliable. And that's true. A concrete weather forecast becomes very unreliable a few weeks ahead. No one can predict weather forecast in a month's time. However, we are pretty good at predicting averages. And we know that these models that predict these averages, they are reliable. We can tell you that it's going to get warmer. I cannot tell you that on the 5th of November next year it might be freezing, it might be 25 degrees. But I'll tell you, if we average over the next 5 years, it's going to get warmer. So these models, and this I think is also important to bring across, these models depend of course on the data we put in, on the different cooling and warming factors, and the science usually is good. We're pretty good at telling you how warm it gets, but we're not good at predicting how you react. So humanity is very complex, and societies are very complex. And societies can react by mitigating in their home country. They can decide that they would emigrate. And that's something we cannot predict. So the way things work is that we have energy scenarios, which means, for instance, how do we generate energy? So how many greenhouse gases do we emit? And how much of that goes into the atmosphere? From that we make climate models, which predict the global temperature rise. These impact models predict impact on human welfare, but then we're not very good at predicting how societies react to that. And that's actually what makes it or breaks it. So, if a society decides, let's deal with it, we're fine. If a society decides, let's, come and visit, let's all go to Norway because they're a bit cooler than us, then we have a problem. So this is just an example to show you that this is tough. It's not an easy science. So these are different models. Initially, you're just modeling the atmosphere, then including land surfaces, including ocean and sea ice, then including sulfated aerosols in the atmosphere, other aerosols, carbon cycle, dynamic vegetation, that, for instance, you have these annual cycles in the north and the southern hemisphere, because when everything is blooming, it absorbs more CO2 than in the winter when everything is dead. So it's rather complex, and it gets better. But that means that all these models, they do have a certain variability and only a certain predictive power. But if we now compare all the models, so these are different models that have different kind of fancy inclusions of factors and different complexity, then if we compare with what we would expect if there is no additional CO2 emissions, it doesn't matter which model we take. They're all predict an increase of the temperature rise. And actually, these are the more optimistic models where we might end up with 2 degrees. Most of the current models think they will end up likely there. But you can argue whether one model is better than the other, but qualitatively, they all predict that it's going to get warmer. Now, I hope I've convinced you that it's really worth doing something about this, and I hope I've also convinced you that it's us that can do something about it. It's not, the Earth that generates more volcanic eruptions, that generate more methane and what have you, but it's really us that have changed it. So we are also the people that can do something about it. And now comes a little bit a reflection to my own faith. Why do I feel compelled to do something? So, when you read the Bible, there are different parts of the Bible that speak to you. And something that I read is in Romans 5:5, God's love has been poured out into our hearts through the Holy Spirit who has been given to us. And then in Ephesians 3:7, so that Christ may dwell in your hearts through faith. And I pray that you, being rooted and established in love, and finally in 2 Corinthians 9:7, each of you should give what you have decided in your heart to give, not reluctantly or under compulsion, for God loves a cheerful giver. So the first step is God's love has been poured into our hearts, and so that we may root it in his love. And then this leads to the third step, namely that we give cheerfully what we can. And what I have decided to give from this is my time to inform people about climate change and to possibly do something about it. So the way I feel about this is that it is an expression of my love to do what my heart feels, and that it is to give not my money, but my enthusiasm, energy, and time to something about climate change, and do it cheerfully. I hope you got the message across that I'm doing this. I like to do this. I'm not someone whipping me on the back saying like, you need to give talks about climate change. No, that is something that I like to do, but it's something that is rooted in my own belief, in my faith. So what can we do? What can we do with climate change? Climate change is there. Climate change is man-made to a large extent. What can we do? Well, there are two approaches that we can do. There's one which is mitigate, and one is adapt. So adapt, we have to do anyway. So essentially protect our people. So we're building better houses. We are building dams. We are building dams against rising sea levels, which, if you go to East Anglia, is quite an important thing. However, in the long term, the solution will be not to build higher walls. The solution will be to reduce our carbon footprint and to reduce the cause of global warming. And there are different approaches on how to reduce the carbon footprint. So the most well-known one is CO2 neutral energy production. Wind power, biofuels, solar, water. Like the UK is pretty good on wind power and water because you've got lots of wind, and at least in the ocean we also have the tides. On a good day, Germany produces 150% of its energy consumption by renewable energies. On a wind still, foggy, cold November day, it's about 25%. So at the moment, while average over the year we might get there, a big challenge is how to store the energy. And that is a big thing. So if we have CO2 neutral energy production, it unfortunately does not run as reliably as a power plant that burns coal or a nuclear power plant. So one of the big difficulties for this is we need to somehow store the energy, batteries, or you pump air under high pressure in a cavern or stuff like that. There are many things. You pump up in the Alps, you pump up water. There are a lot of ideas about that, but even better is, of course, we reduce the energy consumption. We don't need that. So if we can reduce our energy consumption, then we don't need these problems. And the final thing is recovery of waste heat. And the two things I'm going to talk about is this. I'm not going to talk about CO2 neutral energy production. There are a lot of excellent people also in Cambridge doing research on that. There's a lot of advances being done there, but today I'm going to focus on the latter 2 points. So reduction of energy consumption. Now comes my own research, so the stuff I'm talking about from now on is where I'm actually formally competent. The other things is I learned and read myself, but the stuff I'm talking about next is actually things that I actually research on. So my research field of nanotechnology, information technology devices, is actually to blame for a lot of energy consumption. So this is the power consumption of information technology from 2006 to 2025, the prediction, and they predict that we have an increase of about a factor 10 for the energy consumption in these 20 years. And actually 2018, we are at 2 trillion kilowatt hours, so pretty much exactly on that curve. And to put this in perspective, that 2025, this corresponds to 15% of the global power generation, which is 6% of the total energy consumption in the world. And that is very similar to the power consumption of traffic. So this means that all your IT devices, your mobile phone, your iPad, your iPod, what have you, computers and so on, together take the same amount of energy as all the ships, planes, cars, trains together. And that's quite significant. And it's not just what you carry, but you know who is one of the largest energy consumers in the US? Any idea? Google. Yeah. And you know why? Not because they have a fancy headquarters, which they also have, but because they operate computing centers. And the interesting thing is, you know how much of the energy that the computing center needs is actually going into computation? About half. And where does the rest go? Cooling. So half of the energy is needed to cool the computers. So if you were able to reduce the power consumption of the computer by a factor 2, you'd also halve the cooling. It's even non-linear, so it's even better than that. So this means reducing the energy consumption of IT devices will make a big difference. So what's the problem? Why does your computer and even your iPad, iPod, why does it get hot? One of the problems is memory. So your computer, this is your computer, very simple schematic view of your computer, contains a logic CPU, a central processing unit. Then it contains some so-called volatile RAM, random access memory, which stores the information during its operation. And then it contains some non-volatile memories, such as hard drives or flash drives, and the display. And let's say my computer right now, it's not doing anything, but it still needs energy. And it needs energy because this memory here is volatile. It forgets what I wrote into the memory after micro or milliseconds. That means I have to rewrite it thousands of times per second so that it doesn't forget. So this means the computer is hot even during standby time. And we would like to have a computer where this memory here is replaced by a non-volatile memory so that it doesn't need to be rewritten if I don't want to change the information. So this one has to be rewritten even if I keep the same information in there all the time. And this then leads to, for instance, for the motherboard of my computer, that takes about 300 milliwatts, that if I replace the DRAM, so the volatile random access memory, by a non-volatile memory, this reduces the power consumption by about 60%. If I replace so-called cache, that's fast random access memory, which is also volatile, by a non-volatile memory, I can decrease it by another 40%. My CPU is pretty good. I'm not working for Intel, but this Intel power gating technology means that the computer, when it is not doing anything, it switches off 3 of its 4 cores and goes to sleep and reduces the power consumption a lot. So the processor is pretty good, but the memory is not good. Another factor is the display. NITT means not in this talk, but if you have like a Kindle to read, you know that your Kindle lasts for 3 weeks without charging. So there are ways to have low power displays as well. But that's not my research, but that's also important research. So what you would like to do is you'd like to replace this volatile memory, which keeps on being refreshed all the time and keeps the computer busy, by something non-volatile. And there are different types of digital data storage. So there are these fast, volatile memories which are reliable. Then you have flash, which is non-volatile, but it's slow and limited endurance. You have the magnetic memories, which are massive, cheap, slow, but if you drop a hard drive, it usually breaks and has mechanical motion, which means it also it uses a lot of energy. So hard drive spins and mechanical motion is bad because it takes up a lot of energy. So what you would like to do, and this is our current research, you'd like to develop a memory with high storage density, high reliability, long endurance, fast writing and reading, and non-volatility in order to have low power. And the scary thing is that we can do all of this, but we cannot do cheap. So now comes one of the big things that us scientists are always very bad about. There is more to having a solution for a problem. You need to have a solution for a problem which actually has a market. So the majority of the people are not willing to spend an extra $100 on their laptop just because it uses a lot less energy. So if you make such a solution, it also has to be competitive on price. And that is very tough. And that's something we are not so good about. It's something to think about, and it's something I learned kind of the hard way because I worked also at IBM for a while. And at IBM, I had always tons of great ideas, I think. But then when it came to realization of these ideas, you needed to make sure that the idea was solving a problem in a way that it was cheaper and better than the incumbent technology. And that makes it very, very tough, because if you look at current magnetic memory, a hard drive, you can buy a terabyte of data storage for $50. And it is extremely challenging to do anything that has a similar amount of storage capacity for that price. And so this means we need to somehow come up, and we need to keep in mind when we look for solutions that are low power, that they're actually competitive in the market. And that is something that we don't teach our students, but it's something that we won't solve the problem if it's not competitive. All right, and that brings me to the last part, which is recovery of waste energy. So obviously your computer gets hot, and that's waste energy. Obviously your car engine gets hot, that's waste energy. Any idea how much of the total energy consumption in a society goes into heat, into waste energy? 5%, 20%, any idea? 40%, yeah, so not so bad. So if you look at this, this is the US energy use in 2011, so nearly 100 quarts, and you see how much is waste energy and how much is used energy. You see more than half is waste energy. More than half of the energy that is produced goes into heat and not into what we want it for. I mean, very bad example are incandescent light bulbs. A light bulb primarily generates heat. It generates also a little bit of light, that's why we use it, or we used to use it, but primarily generates heat. LEDs are much, much better. They produce largely light and also a little bit of heat. So that's a good example where we've gone from primarily heat to primarily what we wanted. So here's just to explain this. These are the different sources of energy: solar power, nuclear power, hydro, wind, geothermal, gas, coal, petroleum, biomass. So natural gas, coal, petroleum, these are the fossil fuels. And then most of the petroleum goes into transportation, so that's your car. A little bit into industry, most of the gas goes into industry, but also commercial and residential. And most of the energy from nuclear and coal goes into electricity generation, and most of that goes into residential and commercial. So we need a lot of electricity, we don't need so much gas, for instance. And now the problem is, where does all the rejected energy come from? Look at this, that's a scary number. You see, out of our transportation, only 6.76 go into, that's driving, 20.3 go into rejected energy. So most of the energy from a car goes out by the exhaust. For electricity, it's already a little bit better, but electricity generation is also not good. Making electricity out of coal is not a super efficient process. So this more than half means there's a huge potential. There's a potential of half of our energy that could be saved. Obviously, it's not easy, otherwise we'd be doing it. But let's come back to the transportation. So here's my car. So this car uses fuel, petroleum, and about 70% of the energy stored in the petroleum goes down the exhaust, and 30% is used to arrive at the wheels. So this means that we need to somehow use these 70% which go out the exhaust. And there are actually ways to do that, and now comes really one scientific slide. So there is actually a way to convert heat into electricity. It's a so-called thermoelectric element, where we have a hot end, which is the exhaust, and a cool end, which is the outside, just the air, and that makes a battery. So these are two people that worked on that, Jean Pétier and Thomas Seebeck, and they generated, in particular Thomas Seebeck, he made a device where one end is hot and one end is cool, and out comes energy. So any temperature gradient, so where it's hot on one side, cold on the other side, could be used to generate energy. And that could also could be you. Like if you have a coat, my coat on the inside, I can tell you right now, is a lot hotter than on the outside. So if I use that temperature gradient, I could charge my mobile phone with it. So what are these? How do these things look like? This is a typical device where on the top it's hot, at the bottom is cold, and here comes the energy. So this works. There are these modules you can buy. And so then the idea is that we can use this 70% which is rejected and hopefully increase the amount that goes into the exhaust by half. So that's an idea, or at least a third or so, that goes into the exhaust can go back to the wheels or could be used to power your stereo or something else. So that is something that is semi-realistic, and that actually allows you to improve the fuel efficiency of your car already by something like 10%. But it still means that we are losing a large part of the energy that is taken from fuel. And that has to do with the fact that fuel engines are inherently inefficient. So in order to be disruptively better, the way forward is you need electric engines. Electric engines are inherently much, much more efficient. So go to an electric car, and I believe that in 50 years we will not have any petrol-powered cars, because we can't afford to waste half of the energy stored in fuel, because there's not so much left, and because it is ridiculously inefficient for CO2 emissions. Okay, so this is one example, so where people are working on, and I think has a lot of potential. Here are some advertising slides. So here are the boots, which on the inside are hot, the rubber boots, on the outside they are cold. Powers your mobile phone. You can use this in car seats, and where it's actually used is in a spacecraft. So a spacecraft actually runs by that, but in a very special design. They have a nuclear element that is hot due to radioactive decay, and on the outside in space you got pretty cool temperatures. So that temperature gradient is used to power this spacecraft. This is Cassini, which is did fly to Saturn. But yeah, so here you see that you can use this even to locally, for instance, power some medical devices or a watch, because usually on your skin it's also hotter than on the outside. Or it works also if your skin is cooler than the outside. All right, so that brings me to the end of my presentation. So here's a little bit of further reading. There's an excellent book from David McKay, who unfortunately passed away. He was here at Cambridge. Sustainable Energy Without the Hot Air. It's still an excellent book. I can recommend it for everyone to read. He gives some very sound arguments which are easy to understand if you don't have a scientific background, but they're correct. Sometimes also arguments which are easy to understand are wrong, but he actually has arguments which are correct and easy to understand. Mark Maslin, he wrote two nice reports on climate and global warming. There is a climate science special report from the National Climate Assessment in the US. And then for Christians amongst us, I think there's a very nice website, Why Should Evangelical Christians Care About Climate Change? So fortunately, I've never been attacked about this, but colleagues of mine that give similar talks have been attacked, that they are the devil's advocates, saying that it's climate change is man-made. My own work, so we have two publications, the Sandton Declaration of Sustainability, and a little report as well, Sustainable Technology Leadership in the Field of Mobility and Buildings with a focus on energy consumption, with the policy brief and the policy paper. You find these both on our website. And for low power green IT, if you're interested, we wrote a little chapter in this book, Handbook on Spintronics, on low power magnetic memory devices and on waste heat recovery. There's a book by Mr. Bell, and also the Department of Energy in the US has a waste heat recovery resource page, which I think is quite good. And so with that I come to the end. So these are all kind of the buzzwords, and there's one important buzzword for me, which is essentially faith. And I hope you enjoyed this, and I'm looking forward to the discussion. Thank you.
Mathias, thank you very much. We've got plenty of time for discussion to pick up on some of the points that have been raised. Liz, you'll bring the microphone. Wait for the microphone to come to you.
Thank you very much. One or two things you haven't mentioned. You didn't emphasize very much the role that nuclear power stations could do.
Mm-hmm.
The other thing, have you ever considered LENR? LENR.
LENR, what's that?
Don't you know?
LENR?
Low energy nuclear reaction.
Okay, so nuclear power is an interesting concept to generate energy, and generally it has, in terms of power and in terms of CO2 emissions, big advantages because it is CO2 emission, largely CO2 emission free. I mean, if you do the total calculation, you have to take into account how much CO2 is emitted during the building of the thing, and that's not so small, but the actual operation for the energy production is largely CO2 emission free. It has, of course, other disadvantages, as we saw in Fukushima. It has also disadvantages that, and I think that's for us the most difficult one, is long-term storage. What do we do with nuclear waste? When I was younger, a high school student, I thought we just shoot it into the sun, which would be really good. The problem is that the way there is not very safe, and if it goes awry once, not good. No, I mean seriously, I think nuclear is useful because it provides a very stable and inflexible amount of energy produced. So for a base load, it's very useful. But I think it's also not something that we, at least but that's now my personal opinion, without a solution for the radioactive leftovers, I think we have a problem because they will be radioactive for many thousands of years, and I really don't know what our society will do in many thousands of years. And I think it's a legacy that I would not like to leave for my two children and their offspring eventually, because if people start digging in 1,000 years and they find this and think, oh, that looks nice. Yeah, so I think it is a mix. I think in this book, Energy Without the Hot Air, I think there was a valid point in saying, Michael was saying, it all needs to add up. In the end, it has to be a viable solution, and I think at the moment we don't have a single solution that will solve everything. And so I think nuclear will be there. I think in Germany it will be phased out gradually. Because it has disadvantages, not just psychological. There's a lot of psychological blah, blah, blah. But there are actually, I think, objective difficulties such as the radioactive leftovers. There are other approaches to using nuclear power as well, but I think they all entail the problem that you have in the end some radioactive leftovers.
LENR, there's no radioactive leftover.
Okay.
Have you not heard of it?
No, I mean, I know there's this idea of this Paulo Rubio that you can use protons to shoot at radioactive leftovers and thereby make it into some very short-lived radioactive fragments which will decay very quickly, so you don't have that problem anymore.
No, low energy nuclear reaction is different.
Okay.
And even the CIA put money into it.
Okay.
It's developing in several countries
Okay.
at the moment.
Well, it's, you know, I mean, I'm very interested in here. I mean, I'll look it up after this.
Okay.
One question just here and then further back. Wait for the microphone.
Thank you. Talking about nuclear energy, I'm from Japan, but and I ask you because I think you Cambridge scientists top, and Japanese people are naive to what real scientists said. So you're very influential to Japanese condition in future. But I heard some Japanese some scientists said nuclear plant needs a lot of water to clean down, to cool down the system. And in that sense, it warm up a lot of sea water, and you know, it might not produce CO2 like carbon energy, but in that sense, not only in terms of atomic waste, but in terms of direct influence to global warming. As well. Yeah, thank you. 分かってください。
東北大学で勉強しました。
Oh yeah.
So, yes, that's true, but that is also the case for other power plants. Because the way that we generate energy out of fossil fuels is we burn fossil fuels, which heat water into steam, and the steam drives a turbine. And that's the same, by and large, for a nuclear power plant. So this problem that you end up with steam coming out of hot water, coming out of the power plant, is not a particular problem of nuclear power plants, but it's a general issue with using heat to generate energy. And this is essentially lost energy. So if you go to a coal power plant, it has these big cooling towers where you have a lot of, now my father called this, they make clouds. They do. And this is lost energy that goes out of the chimney. But that is not something to do with nuclear power. That's a general issue of using heat to generate energy. So there are other ways to generate energy which don't rely on heat, which, you know, like for instance solar power, where you have a direct conversion. There are also other ways where you can use hydrogen directly to make heat without going via, to make energy without electrical energy, without going via heat. But everything where you go via heat, you have this inefficient step of turning the high pressure water vapor into a mechanical rotation in a turbine, and the water vapor afterwards is not completely cold, but still goes out with a relatively high temperature, and that is lost energy.
Question over there.
Thank you very much for your talk. I'd like to ask a question about the kind of discourse publicly about climate change. So the voices that I listen to tend to fall into one of two categories. And these are kind of academics and friends at the same time. On one hand, you have a kind of apocalyptic kind of take on it, that this is going to happen, and the only way it will change is a dramatic change to our lifestyle. So people who tend to advocate that position would be very kind of interested in sustainable living and kind of food production and things like that. And then on the other hand, I have people who are more interested in the technology and kind of say, no, we will kind of overcome it, and people would be very interested in your line of work and our kind of solutions to reducing the problem. Where would you fall between those two kind of camps? Do you think, obviously to be doing your work, you must be optimistic about our capacities to come up with solutions for this problem? But would you tend to kind of, trying to think what the direct question is, do you think, are you quite optimistic about technological solutions to this, or do you think there also has to be a passionate kind of discourse about lifestyle and those kind of changes?
Yes, so I think the most obvious sign that I'm not completely pessimistic is that I just had my second child. So I wouldn't, I wouldn't set children into the world if I wasn't optimistic that they could have a good life. I mean, essentially it's a little bit about here these two things, mitigate and adapt. And both comprise both aspects, i.e. I think we will not be able to have a good life without using technology to compensate for some of the things that are happening anyway. Because, you know, climate change already has happened. The number of typhoons is going up, the number of droughts is going up. So this will happen anyway. So there is a need for technology to compensate for that. I mean, I believe that in Germany in 20 years' time, everyone will have air conditioning. This just will happen, I think, because just otherwise the life would not be able to be lived the way it is, and the mortality would go up. Whether it's a good thing or a bad thing, it remains to be seen, but it's probably not a good thing, but I think it'll happen. So I believe in technology, you know, partly because I'm also a scientist and a part engineer myself, but nonetheless, it's a question of how much do you want to invest in this technology to compensate for the problems arising due to climate change. As I said, if we have a 5-degree increase in temperature rise, we will be using, and I'm not putting any numbers, some people say a double-digit percentage of our GDP just for disaster mitigation and disaster recovery, because we will have all these floods and droughts and storms. And then at some stage it becomes unsustainable. You know, if our society is primarily preoccupied with fixing disasters, it's not good either. So I think, you know, I think we need a two-pronged approach where we have both a reduction in CO2 emissions to keep the level of natural disasters at a level that we can deal with, at the same time improve technology to deal with them better. So none or the other will work, because we're already too far that we cannot, you know, even if we stopped emitting CO2 emissions today, it would not, you know, it wouldn't be that our temperature in 2 years is back to where it was in the beginning of the 20th century. It's not going to happen. So, yeah, so I think we need both. But let's say I'm an optimistic person. Maybe I'm still relatively young. So I think humanity is not doomed. So I'm not apocalyptic. I don't think that my children will necessarily live in poverty and disaster-stricken areas and what have you. But I think it does require us being aware of what we're doing and always balancing things and making sure that when we take decisions, we are aware of the long-term implications. I think this is the biggest thing that we need to teach the children, the general public, that the decisions we take today will affect us when it comes to climate change over the next 50 years.
One from Hugh, and then probably a final question over there.
Thank you for your talk. I want to change direction very slightly. Buried in some of the electronics that you talk about are some very rare chemical elements. Extracting these is very energy intensive in processing them. Have you taken account of this in the total energy budget that you're talking about?
Yeah. So this is a very valid point, and it's very valid for two reasons. One is that it is indeed sometimes energy intensive to take these, you know, for instance, rare earth materials out of and process them. The other thing is that, you know, because they're rare, there's simply not a lot of it, and when it's all mined, it's gone. So the two things that we're doing is we are replacing some of the most expensive materials by compound materials that comprise atom species that are not as rare and easier to get to. So for instance, iridium is a very rare metal, and there's a new project that replaces iridium by other compounds that contain copper or aluminum or things like that. So that's one thing. On the other thing, people now do a calculation, what they call is from gate to grave. where you start with the fabrication of a car that also takes energy, including getting the raw materials, and ends up at the power that is consumed in order to disassemble the car if you recycle it or whatever. So that is a complete life cycle. So that's taken into account. And one of the key things that we need to do is recycle better. I think it's absolutely crucial that we recycle IT devices and that we build IT devices in a way that they can be recycled easily. I think this is something we're extremely bad at the moment, because everyone's the cheapest, highest density, fanciest. But I think in the mid-term, also the companies, like I know Samsung now, Samsung is looking at how they can build devices that they can relatively easily recycle, and they want your Samsung mobile phone back. They don't want you to chuck it into the bin. They want it back because they can get back the expensive materials they put in the first place. So this is happening, and it's not happening because just they like a green culture, but because it's cheaper.
One final question over there.
Thank you very much for your talk, very interesting. I've been driving a battery electric car for the last year, and it does something like 6 kilometers to the kilowatt hour. And of course I recharge it from the grid. Am I saving the environment any emissions?
That depends very much on where the energy comes from that you take from the grid. So I also have a hybrid car that runs for a few miles on total electric car, and I bought from my energy company a tariff that claims to be CO2 neutral. Obviously, I can't know where the electron was produced, but on the average, it's correct. So they are only allowed to sell this as a CO2 neutral tariff if it's really CO2 neutral. Then the question is, does your car, because it can so it's my hybrid car that can take both electricity and fuel, is it so much more complex in the fabrication process? It took more energy to produce. Yes, it does, and then you have to take a life cycle analysis. So it depends on how much you drive, depends on which conditions you drive. I cannot calculate this for your car, but let's say I think it's possible. I don't think that buying an electric car means that the energy consumed to build the car was so much higher that over the lifetime of the car you can't get it out anymore. I think that's not the case. I think it's pretty clear that you can save, but obviously if all the energy that you buy is generated by brown coal, which is in Germany very popular and is one of the lowest energy density fossil fuels, then I think, I'm not sure how much you're actually saving. But if you, and this is also a good thing about these cars, and usually you can recharge the car when there is renewable energy available. At night, when the big consumers of electricity from industry are offline, then then it might be easier to use that and store energy. And actually, cars are fundamentally a possibility to balance out and compensate for the fluctuations of renewable energies, because for the car you can simply say the electricity is super expensive if there is little available and super cheap if there's lots available, and then people will charge the cars when it's cheap. Yeah? So I think this is a good way forward, and I can commend you for driving an electric car. Also, I just like the feeling to drive an electric car. I think it's just good. Okay, maybe leave it at that. No advertisements.
Okay, on that note, I think we'll draw to conclusion today. Thank you very much for informing us and for challenging us at the same time. You join me in thanking Mathias.